Hi everyone, welcome to the physics review session. So today we're going to review the chapters that are going to be on the final exam. And I'm going to do that by examining some common physics problems, including the inclined plane problem, projectile motion, and a few other common physics problems. So projectile motion looks a little bit like this, right? So let's say you're on a flat ground, you kick a ball. Oh, some people are in the waiting room. Okay, so you kick a ball at some angle. We'll call that angle theta. And you kick it with some initial velocity. We'll call that v naught. Okay, so there's a lot of questions you can ask about this simple physics problem. The first question you can ask is, what are the components of the velocity of this ball? Well, that's pretty easy to figure out, right? If you have this initial velocity v naught, how can you figure out the vertical and horizontal component of the velocity? Well, it's as simple as using your trigonometric identities. So the vertical component of the velocity is just going to be v naught sine theta, right? So v naught sine theta. And the horizontal component is going to be v naught cosine theta, right? Okay, and so now we can ask a bit more complicated questions. We can ask, how far is this ball going to travel? So let's go ahead and solve that. What is the range of this ball going to be? Okay, so we have this ball. Okay, so it's going to go in a parabolic trajectory, and we want to figure out how far it's going to travel. What is its range going to be? So to answer this question, the first thing you need to know are your four kinematic formulas, right? So let's go ahead and write them down. So the first formula you should know is the final velocity is equal to the initial velocity plus however much you're accelerating times the time you've accelerated for. So that's Vf is equal to Vi plus At. Another formula that can be useful for figuring out distance is the amount of distance you cover is however much your initial velocity is times the amount of time you travel plus half your acceleration times your time squared. So d is equal to Vit plus half At squared. Now if you don't know your time, there's another equation that can come in handy in some cases, and that's that your final velocity squared is equal to your initial velocity squared plus twice your acceleration times distance. So as you can see in this equation, we have no mention of time, but we can still figure out distance or final velocity. Okay, I can't remember what the fourth one is, but it's probably not important. But if anyone remembers, just let me know and we can derive it. Okay, so let's see, how can we figure out how far this ball is going to travel just by using these equations and using what we know about the initial velocity? Okay, well here's how we can do it. So first thing you want to figure out is how long is your ball in the air, right? That's the first question we want to answer. How long is the ball going to be in the air? To figure that out, we can start by using this equation. The first equation, the final velocity is equal to the initial plus At. So let's go ahead and employ that. So how long is ball in the air? Is ball. Okay, so let's go ahead and do that. So Vf is equal to Vi plus At. We're going to apply this only for the vertical component of the velocity. So let's go ahead and add in that index here. So Vfy is equal to Viy plus Ayt. Now here's something funny that happens. When the ball is going up, right over here, its vertical velocity becomes 0, right? Its Vy becomes 0. And why is that? That's because gravity has been slowing down the vertical velocity of the ball for the entire trajectory over here. And then the ball changes direction and it starts moving downwards. And so at this point, the ball's vertical velocity is 0. Right? So we can leverage that fact to figure out how long the ball is going to be in the air for. So let's go ahead and do that. So the final velocity of the ball at this point, at the halfway point, is going to be 0. Okay. The initial velocity of the ball is going to be v naught sine theta. Okay, v naught sine theta. Oh, we've got this in the way. Okay, v naught sine theta plus, what is the vertical acceleration? That's just the gravitational acceleration times time. Right? Okay. So now all we have to do is solve for t, right? So let's go ahead and solve for time here. So we're going to have t is equal to v naught sine theta over g. And if it makes you more comfortable, you can of course plug in numbers here, but the math is going to be the same, right? Now this is the time, you should realize, that it takes for the ball to reach the halfway point. The total air time of the ball is going to be twice this, right? Because this is the time, this time is however much it takes, however long it takes for the ball to get up to this halfway point, right? When its vertical velocity reaches 0. For the total air time of the ball, all we have to do is double it, right? Because it takes the same amount of time for the ball to get up here as it takes for the ball to get back down. Okay, so that's the first question we answered. How long is the ball in the air for? And this is the answer. The second question we can answer is the one that we asked originally, which is how far does the ball travel? What is its horizontal range? So what is... Oh, by the way, if anyone has questions, you can just unmute your mic and speak up.
Why didn't you negate the acceleration? If the ball is going up and acceleration is like pointing downwards, shouldn't it be negative?
That's right. That's right. Unless you want negative time, which is not possible, you should negate this. Yes, that's right. And actually, if you did make this positive and you solved for time, you would have gotten something negative. So you would have known something is up. So yeah, that's right. This should be negative here. Okay, so thanks for pointing that out. So moving on, what is the range? What is the horizontal range of the ball? So how can we figure that out? Well, we know how long the ball is in the air for, right? And we know what its horizontal velocity is. So if we just multiply those two quantities, we can get its horizontal range. Right, okay, so let's do that. So the distance is going to be simply its horizontal velocity times the amount of time it spends in the air. Recall that there is no horizontal acceleration, so the ball's horizontal velocity is not going to change for the entire trajectory, right? So if the ball is going 5 meters per second to the right in the beginning, it's going to be going 5 meters per second up here at the top, 5 meters per second up here, down there at the bottom, right? So there's no horizontal acceleration. That's why our horizontal distance formula has no acceleration involved, right? It's very simple. Okay, so let's go ahead and plug in stuff. So what is our initial horizontal velocity? It's v naught cosine theta, okay? So v naught cosine theta times our time, which is 2v naught sine theta over g. Okay, and now if you want, you can simplify this, or you can plug in numbers, whichever one you prefer. I'm just going to simplify this quickly. This is 2 sine theta cosine theta over g. And that's going to be, what is that? V naught squared sine 2 theta, I believe, over g. So this is going to be the total horizontal displacement of the ball. Okay. Okay, and the final question that we can answer about this projectile motion problem is how high up does the ball go, right? That's a pretty reasonable question to ask. What is the maximum height achieved by my ball? And for that, you can use this equation. Actually, you can use a number of equations, but I'm going to use, I'm going to use this maybe. Okay, let's try using that. So what is the max height? What is max height? Okay. Okay, so how can I figure out the max height that my ball goes? As I said, we can use a number of equations. I'm going to try to use this one. So let's see. The distance is equal to VIT plus half AT squared. Okay. We want to find the vertical distance, right? So let me just add that over here. T sub y, VIY, AY. Okay. So the maximum vertical distance is going to be, well, what is the initial vertical velocity? That's going to be V naught sine theta, right? So V naught sine theta. What is the time that the ball spends in the air? Well, we figured that out before. It was whatever this is, 2 V naught sine theta g, 2 V naught sine theta over g. And I'm going to learn from my previous mistake. I'm not going to make gravity positive, but you know, depending on your choice of orientation, gravity can be positive or negative. I'm just going to make it negative here. So minus half g t squared, and t comes from before, 2 V naught sine theta over g squared. So this right here, this mess, is your is the maximum height achieved by the ball. It looks very nasty here, but as soon as you plug in numbers, it should become something reasonable. Okay, so those are the big questions. If projectile motion comes up on the exam, these are typically the questions you'll see. How long does the ball stay in the air for? You can use this equation, Vf is equal to Vi plus At. If they ask what is the range of the ball, you know, how far does it travel horizontally, you can just use, you know, distance is equal to rate times time. And if they ask you what is the maximum height of the ball, you can use this equation, or if you want to get fancy, you can use this one as well. So
are these problems guaranteed to be on the exam?
I don't know. I'm just practicing here, so I couldn't tell you. Okay, so that's projectile motion in a nutshell. If anyone has questions, you can ask them. Otherwise, we're gonna move on to inclined planes and whatnot. Yeah, I don't know if there's something in the chat. Oh, okay. I think that question has been asked. Why don't you negate acceleration? Okay, so we're going to move on then, unless anyone has questions, on to friction. Okay, so let's go ahead. Move on to friction. Okay, so the typical friction problem involves a box on a table. Okay, something like this. This box will have some mass. Okay, that's too big. This box will have some mass. And let's go ahead and just draw some of the forces that are acting on this box. First is, of course, its own weight. Right, that's going to be mg. Then is the normal force, right? So that normal force is going to be upwards. Oops. Okay, and it's going to be equal in magnitude to the gravitational force. And then if the box is moving and there's friction on the table, you'll also have the force of friction, right? That is slowing down or hampering the box's movement. Right, so force of friction. Okay, there's more people in the waiting room. Let me just admit them. Okay, so question is, what is the force of friction? Force of friction, well, it makes sense if the box is heavier, right? Then the force of friction should be greater, right? If the box is heavier, then the force of friction should be proportional somehow to the box's mass. And indeed it is, right? Force of friction is equal to some constant, mu, times Fn, where Fn is the normal force, right? So in this case, for example, the force of friction would be mu mg. So let's go ahead and now, that's pretty much friction. and we'll consider friction problems later. Now we're going to move on to inclined planes. By the way, if you guys haven't noticed, I'm doing this improv, so I haven't prepped at all for this, but yeah, I'm just coming up with problems that are important and might be on the exam. So we did projectile motion. This is friction problems. Now let's think about inclined planes. So these are always fun. So this is an inclined plane, right? And usually they'll be at some angle theta, and you'll have some box of mass m here. And first let's analyze this situation first by drawing a free body diagram. So what forces are acting here? Well, first of course is gravity, right? We have the force of gravity downwards on this box. And we have the normal force, right? So the normal force is pointing upwards, or is it, right? Does the normal force always point upwards, opposite to gravity? Well, no, right? The normal force is perpendicular to the surface that you're in contact with. In this case, the surface is this inclined plane, and so the normal force will actually be in this direction, right? Perpendicular to the surface. Okay? I think someone wrote something in the chat. Oh, Sabir, yes. Yes, I am recording, so yeah. And I'll send the recording to everyone after it's over. So, as I was saying, the normal force is going to be perpendicular to the surface. And so how can we figure out, how can we decompose this gravitational force? Okay, we've all seen that this gravitational force is decomposed into one that's parallel to the inclined plane and one that's perpendicular, right? Fg perpendicular. But how can we figure out what those are? What the values for Fg parallel and Fg perpendicular are? Well, here's how we can do it. First of all, we know that Fg, the gravitational force, is of course simply equal to the mass of the box times the acceleration due to gravity. But how can we figure out Fg parallel and Fg perpendicular? Well, we know that they're mg times either sine theta or cosine theta. And you might forget which one it is, right? Is Fg parallel sine theta or cosine theta? Well, to answer that question, you can either derive the formulas on the spot, or you can think about extreme scenarios, right? Think about extreme scenarios. Oh, okay? So let's say you have a really steep incline, something like this. Okay, no, that's a little too steep. Let's say you have a really steep incline. Okay, and here's your box, right? And this is maybe some angle, really close to 90, maybe 80 degrees. Okay, now clearly the Fg parallel component is going to dominate the acceleration of the box here, right? The Fg perpendicular component is not going to be as big, right? Intuitively you can see that, right? So whatever Fg parallel is equal to, either mg sine theta or mg cosine theta, it should be bigger than the alternative, right? So let's see. When you bring sine of theta closer to 90, does it increase? When you bring cosine theta closer to 90, does it increase? Well, as theta increases, cosine theta decreases, right? So we know Fg parallel can't be this one. And so therefore Fg parallel must be mg sine theta, right? So that's how you can just use your intuition to kind of remember what the formulas have to be. So going back to this free body diagram, Fg parallel is mg sine theta and Fg perpendicular is mg cosine theta. And now let's say we want to, oh, people are in the waiting room, wow. So now let's say we want to find the acceleration of this system. How can we figure out the acceleration of the box on the inclined plane? Well, this diagram looks kind of messy, so I'm just gonna shift this over. Now we know all the forces acting on this. So let me just come over here. Okay, so here's the box. Okay, here's the box. Oh, sorry, here's the incline, and here's the box, right? And this is at an angle of theta. And our goal is to figure out the acceleration of the box down the inclined plane. So we want to figure out the acceleration. Oh, by the way, if anyone has questions, again, just feel free to raise your hand or just speak up. Okay, acceleration of box. Okay, so how can we figure out the acceleration of the box down the inclined plane? Well, we can consider the forces acting on the box, right? So we know that along the inclined plane, if this is frictionless, there's only one force acting on the box, right? And what is that force? That force is going to be the parallel component of gravity, right? So that's going to be Fg parallel, right? Fg perpendicular, you'll remember, is perpendicular to the surface of the incline. So it doesn't affect the trajectory of the box unless the box is moving up and down, which is not really physical. And the normal force is again perpendicular to the surface of the incline, so that doesn't affect the trajectory of the box. So if this is a frictionless incline, then only Fg parallel affects the motion of the box. So then what do we have? We have F is equal to ma, right? F equals ma is equal to Fg parallel, since that's the only force acting on the box. Let me change this, okay? So that means we have ma is equal to Fg parallel, and we know what Fg parallel is, right? Fg parallel is just mg sine theta. So mg sine theta. So that means the acceleration of the box down this incline is just g sine theta, right? G sine theta. Okay? So that's how you can figure out the acceleration of a box down an inclined plane. Now, what if we add in friction, right? What if we want to spice up the problem a bit and we want to add in friction? So that's slowing down the box. Okay, then let me go ahead and write that down. What would the acceleration of the box be if there's friction? So acceleration So, of course, if there's friction, we expect the acceleration to be less, right? You don't expect the acceleration to be g sine theta, you expect it to be g sine theta minus something, right? We don't know what that something is yet, but we can figure it out. So let's go ahead and do that. What is the acceleration of this box going to be if there's friction? So friction, of course, slows down the box, so it must be acting in the opposite direction of Fg parallel, right? So that's the direction of friction. Okay, opposite to the motion of the box. So that's the direction of friction, but what is its magnitude? How big is the frictional force? Well, recall that the force of friction is equal to some constant, that's the coefficient of friction, times the normal force, right? Now, what is the normal force here? The normal force here is Fn, but it's not the same as mg here, right? Remember, in the simple case, in the simple scenario, when you just had a box on a table, the normal force was exactly equal to the gravitational force. But that's not the case here, right? In this case, the normal force is not equal to mg. Why is that? That's because we have an inclined plane, right? So just going back here, okay, so in this case, the normal force is actually going to equal Fg perpendicular, right? So let's go ahead and plug that in. I'm going to change to a different color here. So the force of friction is equal to mu, and Fn here, as I said, is going to be Fg perpendicular. So we're going to have mg cosine of theta, right? Cosine of theta. Okay, that's good. So now when we employ F equals ma, we have to make sure to subtract friction from Fg parallel. So let's go ahead and do that. So the net force is going to be Fg parallel minus the force of friction, and this is all going to equal ma, right? Because F equals ma. Okay, so let's go ahead and plug in stuff here. So what is Fg parallel? Fg parallel we know is mg, sine of theta, minus the force of friction, which is mu mg cosine of theta, and all of this is equal to ma. Right. So does anything cancel out here? Yes, in fact it does, right? Mass cancels out. Okay, and so that means the acceleration of the system is g sine theta. I factored out the g over there. G sine theta minus mu cosine theta. Okay, so this right here is the acceleration of the box down the inclined plane if there is friction. So now you have to stop and think to yourself, does this make any sense? And remember, we should expect the acceleration to be less than g sine theta, right? Because g sine theta is the acceleration without friction. So with friction, it should be less. And indeed, you can see we have g sine theta minus something. And that something happens to be g mu cosine theta. Okay, so that is that's basically inclined plane problems in a nutshell. Now let's talk a little bit about, so we did projectile motion, we did inclined planes. Let's talk about energy, right? Potential energy, kinetic energy, spring potential energy, all that good stuff. So let's go ahead and does anyone have any questions before we move on?
Are you going to do temperature?
Yeah, if I get to it, yeah, we can do temperature, yeah. If there's time by
And equilibrium?
Yeah, sure, yeah. Equilibrium problems are basically what keeps something stationary, right? So in equilibrium problems, you'll usually want to set the net force equal to 0 and the net torque equal to 0, right? In those two cases, an object is in translational and rotational equilibrium, right? So these two conditions make sure that an object is not moving and it's not rotating, right? So that it has no torque on it. So yeah, if we get to equilibrium and temperature, we'll do that. But for equilibrium, these are the two big things that you want to keep in mind, right? The net force and the net torque are probably
so everything has to be equal to 0.
Yeah, I'm just saying this off the top of my head, but yes, I think that in most equilibrium problems you want to keep something where it is, or you want to keep it irrotational. You don't want it to rotate. And in those two cases, these are the two conditions that apply. If something is not moving, then the net force on it is 0, right? And if something is not rotating, then it has no torque on it, or no net torque. So the net torque should be 0. Yeah.
Thank you.
Okay. So, okay, we've exhausted the inclined plane and projectile motion. So now let's talk about energy. We'll talk about potential energy, kinetic energy, spring potential energy. I'm probably forgetting some, but those are probably the main ones to remember. So let's go ahead and write those down. So okay, so energy. So let's start with the basics, right? Potential energy, that is the energy of position, right? The higher you are up, the more potential energy you have. That's mgh. As you can see, it is proportional to your position, your vertical position. and it's also proportional to your mass, right? So if two objects are at the same height, but one is bigger, one is more massive, that's going to have more potential energy. Kinetic energy is half mv squared, right? That is the energy of motion. The faster you're moving, the more kinetic energy you're going to have. So let me just illustrate these. So potential energy is the energy of position, okay? And kinetic energy is the energy of movement, okay? And if you have a closed system where there is no external forces, then you have conservation of energy, right? So for example, let me try to think up of something on the spot here. Maybe if you have something like this scenario where you're dropping a ball from a cliff, okay? If you're dropping a ball from a cliff, then you can figure out how fast the ball is going over here based on the height you dropped the ball from. And how can you figure that out? You can use conservation of energy, right? So conservation of energy So conservation of energy says that the sum of the potential and kinetic energies initially is going to equal the sum of the potential and kinetic energies finally, right? So in this case, for example, if you drop a ball from a height of h, how can you figure out its velocity at the end? Well, when you drop the ball in the beginning, there's only potential energy, right? We're going to establish this as the ground. This green thing is the ground. So in the beginning, there's only potential energy on the ball. And at the end, when the ball is almost hitting the ground, there's only kinetic energy, right? No potential because it's basically hitting the ground. So that means, using conservation of energy, we have PE initial, PE initial is equal to KE final, right? So we have mgh is equal to half mv squared. We want to figure out how fast the ball is going when it hits the ground. So we want to solve for the velocity. So let's go ahead and do that. The masses cancel out. And so just solving for velocity here, you should get v is equal to square root of 2gh. Right? And so that just comes from the conservation of energy. I think there is something in the chat, so let me look. If there is more than one object, for instance, two boxes or a box and a spring, does each one have a KE or PE? Yes, okay. Let's then do a spring example since someone is asking a question about it. But yes, every object in the system will have its own energy, right? If an object is moving, it's going to have kinetic energy. If an object is above the ground, it's going to have potential energy. But since you asked, we can do a question about spring potential energy. So these are the potential energies and kinetic energies for an object that is in motion or at a certain height. But for a spring, you have a different kind of energy. Let me actually use a dinner marker. It's called elastic potential energy, or whatever you want to call it. A spring's energy is proportional to its spring constant, and it's also proportional to how much you displace the spring. Okay, specifically, the elastic potential energy is half kx squared, right? Where k is the spring constant and x is how much you displace the spring. So for example, if I have something like this, so let me demarcate that here. Let's say we have something like this. If I have a spring attached to a wall. Oh, okay, no, that's not what I want. Why is this? Okay, so if I have something like this, right, and I displace, let's say this is the equilibrium, right? Let's say that's the equilibrium, and I have displaced the box by, I don't know, 5 5 meters. And let's say the spring constant is equal to 2, I forgot the units, but I think it's newtons per meter. Okay, so what is the spring potential energy going to be? It's simply going to be half kx squared, k being 2 here, and x being 5. So in this case, the spring potential energy would be 25, right? So that's just a simple example of spring potential energy. Okay, so, and actually you can use spring potential energy to figure out how fast this box is going to be moving, for example, at the equilibrium. So that's a good idea. Let's try to solve a problem like that. So, okay, so here it is. Let's say let's set up the problem. We have a spring connected to the wall, so something like this. Okay. And let's say this box has some mass. I'll just call it m. Okay, and this spring has some spring constant. I'll call that k. I'll call that k. And let's say that this spring is displaced from the equilibrium by some amount, right? So let's say the spring is displaced from the equilibrium by some amount. We'll call that I'll call it x star. Okay. So we have stretched the spring, and we want to know how fast is this box going to be moving at the equilibrium position. Okay, so in other words, we have taken a spring, we have stretched it, and now we've let go, right? We've let go, and we want to figure out how fast is this box m of mass m going to be moving at the equilibrium position. I believe there's a question in the chat, so in what instance would you have both initial kinetic energy and potential energy? Okay, let's see. You can have initial kinetic and potential energy if you're displaced from the ground and you're moving at the same time. I can't think of any examples off the top of my head, but yeah, that would be the answer to your question, right? So if an object is, for example, if you have something like this, right? Let's say this is your ground, right? If an object is moving up here with a velocity v, then clearly it has kinetic energy because it's moving. But it also has potential energy, right? Because it's some height away from the ground. So in this scenario, for example, this ball would have both kinetic and potential energy initially. So hopefully that answers your question. So returning to the spring problem we have here, our question is, what is the speed of this mass when it reaches equilibrium? I think we have more questions here, so let me pause for a second. Okay, rolling off a cliff. Okay, yes, I suppose that's one example, right? If a ball is rolling off a cliff and maybe you want to find the velocity over here by the time it reaches the end of the cliff. Okay, so coming back to the spring, our goal is to find out the speed of this mass at equilibrium. So how can we do that? So when this mass is fully stretched out here, right? When this mass is fully stretched, what kind of energies does it have? Well, when it's stretched out here, over here, right here, at the instant it's about to turn, it's not moving, right? You can think of this as a ball changing direction in projectile motion, right? At the instant the ball is going to turn, it has no vertical velocity. Same thing here, right? At the instant this mass is about to head in this direction, it doesn't have any velocity, right? So that means the kinetic energy initially should be 0, right? What about potential energy? Well, we're going to consider the potential energy to be 0. Just consider this to be your ground. But what about elastic potential energy? There is indeed some elastic potential energy because this mass has been displaced, right? This spring has been displaced by some amount x star. So there is indeed some elastic potential energy, and it's given by half kx star squared, right? Okay, so now what happens when the mass is at the equilibrium position? So this is equilibrium, okay, and this is a really short spring here, but hopefully you see the point. So when the box is at equilibrium, what kinds of energies does it have? Well, at equilibrium, right? At equilibrium, the box is clearly going to be moving, right? So there's clearly going to be some kinetic energy. In fact, we're trying to find the velocity of the box at equilibrium. So we just don't know what this velocity is, but we want to figure it out. How about elastic potential energy? Is there going to be any elastic potential energy? Well, no, right? It's at equilibrium, so there is no displacement from where you release the box. Okay, so if that makes sense. If it doesn't, just please ask questions. Okay, so the elastic potential energy for the final state of the system is going to be 0. And now we can just set things equal using the conservation of energy and solve. So just to remind everyone what we're trying to figure out, what is the velocity? What is velocity of box at equilibrium? If spring displaced by x star. Okay, so let's go ahead and use conservation of energy. All we have to do is set the initial total energy equal to the final total energy. So let's go ahead and do that. So I'm going to have, initially there's only elastic potential energy, so I'm going to have half kx star squared, and finally there's only kinetic energy, right? So I've got my work cut out for me. So let's go ahead and simplify this. So the halves cancel out, right? And we want to solve for v, right? The velocity, the speed of the velocity of the box when it's at equilibrium. So let's go ahead and isolate v here. So I'm going to have what? I'm going to have kx star squared over m. I'm going to square root this. Okay, so that is going to be the velocity of the box at equilibrium. So just to make that clearer, okay, so that's how you can solve a problem like that. If they give you a spring and they displace the spring by some amount, and they want you to figure out how fast the box is moving at equilibrium. So all you have to do is employ the conservation of energy. Okay, so I'm going to pause for any questions, and if there's no questions, we'll move on to conservation of momentum. Okay, so conservation of momentum it is. So let's see. So what does conservation of momentum say? So conservation of momentum comes in when you have collisions, right? When, for example, two boxes or two balls or two cars are colliding with each other, actually not two cars, that would be inelastic. So if you have something like this, right, two balls colliding with each other, that's when you know to use the conservation of momentum, right? So let's go ahead and write this out. What does the conservation of momentum say? Conservation okay, so conservation of momentum says the following, right? So if I have two balls, one has a mass of m1, so this ball has a mass of m1, and the other ball has a mass of m2, and the first ball has a velocity of v1, and the second ball has a velocity of v2, okay? Then the conservation of energy momentum says this. So first let me actually copy and paste this. Copy, paste, okay. So after these two things collide, they're going to head off in their own ways. Okay, so this guy, let's say V2, is going to maybe head out the other way. So mass 2 is going to start heading the other direction. Mass 1 might head the other direction here. So we're going to have M1 V1 final and M2 V2 final, right? And I should put initial here. So the conservation of momentum says that if you sum up the products of the mass and velocity of this ball and the mass and velocity of this ball, initially it's going to equal the product of the mass and velocity of this ball plus the mass and velocity of this ball after the collision. So writing that out as an equation, we have M1 V1 initial plus M2 V2 initial. So the mass of the second ball times however much it's moving initially is going to equal the mass of the first ball times however much it's moving after the collision plus the mass of the second ball times however much it's moving after the collision, right? So M2 V2F. Okay, so now we're going to solve a problem dealing with conservation of momentum, and we're going to try to figure out how fast a ball is going to move after it collides with another ball. And we're going to use this equation, right? The conservation of momentum. So let's go ahead and do that. So, okay, so let's see, what kind of problem can I come up with? So let's say you have a ball. Okay, let's say you have two balls. One ball is, okay, this is M2, this is M1. This ball is initially moving with some velocity V1, but this other ball, M2, let's say it's at rest in the beginning, right? So this is what we have initial. This is our initial state. Okay, and after they collide, what happens? Well, you can just use your intuition, kind of. You can think, oh, if after they collide, M1 might come to rest, M2 is probably gonna pick up some velocity, right? So this is the final state of the system. It could also be that M1 doesn't come to rest, but yeah, we might want to keep things simple for this example, right? So initially, only this ball M1 has some momentum. And what is its momentum going to be? It's going to be M1 V1. And finally, in the final state of the system, only this ball has some momentum, M2 V2, right? So this problem turns out to be very easy. If you want to figure out how fast this ball is moving after it collides with M1, all you need to do is set these two things equal, and so you'll have V2 is equal to M1 over M2 V1, right? Is that right? Yes. Okay. So that is the velocity of the second ball after it gets hit by the first ball. So we've taken a look at a bunch of force problems. We've taken a look at projectile motion. We've seen how to solve inclined plane problems and inclined plane problems with friction. We've seen how to deal with energy problems that involve potential energy, kinetic energy, elastic potential energy. We've also seen how to deal with conservation of momentum. And so now, let's see what else do I remember from the curriculum. Okay, let's do rotational motion because that's always fun. So how much time do I have? Okay, yeah, I have like literally 5 minutes. So yeah, I'm going to quickly review rotational motion and fluids. But before I do, does anyone have any questions or any problems? Okay, good. Oh, someone put something in the chat. What if the block collides and both blocks move. Okay, what? Move with each other. Okay, yeah, okay, that's a good question. That's a good question. So let's actually do that then. So what someone in the chat is asking, what if you have something like this? You have two balls, right? One is M1, the other one is M2. This one starts off by moving, right? So this one is gonna move and hit the other one, and then they both start moving together. So it's an inelastic collision, right? So let's go ahead and solve that kind of a problem. So this is V1, okay? And this is the initial state of the system. And the final state of the system is gonna look something like this. After these two blocks collide, you can kind of think of it as gum, right? If you have two wads of gum, after they collide, they're gonna stick with each other and move as one object. So now these two things are gonna be moving together with some unknown velocity, and that's what we want to figure out. Okay, so this is simple enough to figure out, or straightforward. Initially, what objects in the system have momentum? Only M1, right? So the initial momentum is simply going to be M1 V1. And what is the final momentum of the system? Well, it's going to be the combined masses of M1 and M2 times their velocity, which we don't know, but we can figure out. And we know via the conservation of momentum that these two have to be equal, right? So if we just solve for V2, what do we get? The final velocity of this combined composite mass is going to be M1 over M1 plus M2 times V1. Is that right? Yes. Okay. So that is going to be, so that's how you solve those kinds of questions. If that, okay. Facts and gravitation. Okay. So yeah, we can quickly go over temperature and gravity. But yeah, to the person that was asking this question, this is how you would probably solve it. Okay. So, and in all honesty, I have no idea how temperature works. So yeah, but I will talk about gravitation if that helps. Okay, so that means in the last few, the last few things I'll talk about are these, gravitation, because someone requested it, gravitation. I'll talk about fluids. Is there anything else? Yes, rotational motion. That's the final thing that I'll talk about. Okay, whatever. Okay, you get the point. So rotational motion. Okay, so let's start with gravitation. Okay, yeah, let's do gravitation first. So let's see. I'm gonna come over here. So let's see. For gravitation, here's one kind of problem that comes to mind. Let's say that this is the Earth, and you're in a rocket and you're orbiting the Earth. One question that I can ask about this system is, what is your orbital velocity, right? So how could you answer that kind of a question? Well, just think about the forces. Oh, actually, first let me write the question down so it's clear what we're asking. What is the orbital? Is it showing up on the screen? Yes. Oh, okay. Okay, so what is the orbital velocity of I don't know, this object. Actually, let's give this object a mass just in case. What is the orbital velocity of the mass m? Okay. So how can you solve this question? How can you figure out the orbital velocity of something that's orbiting something else like the Earth? Well, you can think about the forces in the system, right? So what forces are acting here? Let's think about that. The first force, of course, is gravity, right? Gravity pulling this smaller mass towards the bigger mass. So there's the force of gravity. But there's also another force, right? And that force is what gravity acts as, if that makes sense. What force keeps this object in a circle? It's the centripetal force, right? And in this case, gravity is that centripetal force. So I don't know if that makes sense, but just you can ask any questions if you want. So that's the centripetal force, right? So we have two forces here, the centripetal force and the gravitational force. Okay, and gravity here is acting as the centripetal force, right? It's what keeps my mass in a circular orbit. So that means I can set Fc, my centripetal force, equal to Fg, my gravitational force. And you might be wondering, how is this going to help me figure out the orbital velocity of this object? Well, you're going to see when we expand this out. So first of all, what is centripetal force? It's simply, any force is just ma, right? Centripetal force is m times a, where a is v squared over r. Okay, and gravitational force is g big M small m over r squared, where big M is the mass of the Earth, right? Okay, so I'm going to take a brief break here for 2 minutes, and I'll come back and you guys can try solving this question in the meantime. Okay, so let's go ahead and finish this problem. So we want to figure out the orbital velocity of this object as it orbits the Earth. So we've got the centripetal force equal to the gravitational force, and so now all we have to do is solve for v, right? So let's go ahead and do that. So first thing you notice is that the small m's cancel out, right? The mass of this object doesn't matter, only the mass of the Earth matters. So we're going to have, okay, so we're going to also, if you multiply both sides by the radius, one of these cancels out, and so we're going to be left with the velocity of our satellite is equal to square root of gm over r. Is that right? Yes. Okay. So that is the velocity of our orbiting satellite. Okay, so that's the only problem I remember about gravitation. There's probably more problems, but the big ideas you should probably remember about gravitation are the gravitational potential energy, MGH, and how to deal with maybe these kinds of problems where you have gravity acting as the centripetal force. So if you have any other questions, just yes, you can ask them. So so we covered gravitation very briefly. Let's see, I remembered saying we would briefly cover rotational motion. So let's go ahead and talk a little bit about rotational stuff, okay? So remember, for kinematics, for motion with constant acceleration, we had a few equations. We had the final velocity of an object is the initial velocity plus however much the object is accelerating over some time. That is for linear motion, right? This is for linear motion. For rotational motion, we have something similar but a bit different, right? So this is going to be rotational motion. Okay, so for rotational motion, instead of having linear velocity, you're going to have angular velocity, right? So you're going to have omega f, which is typically given in like radians per second, is equal to your initial angular velocity plus your angular acceleration times your time. Okay, so instead of having velocity, you have angular velocity. Instead of having linear acceleration, you have angular acceleration. Okay, so yeah, these are some formulas that you should keep in mind for rotational motion. Okay, another formula we have is that your final velocity squared is equal to your initial velocity squared plus twice your acceleration times the distance you cover. Okay, let me collapse this here. Okay, so what is the rotational counterpart of this equation? Well, as you might expect, instead of linear velocity, we're going to have angular velocity. So I'm going to have omega f squared is equal to omega I squared plus 2 alpha. And now you might be asking, what is the rotational analog of distance? For distance, we have theta. Okay, that's the rotational analog of distance. Okay, so now what about d is equal to vit plus half at squared? Okay, the rotational analog for this equation, instead of distance, we're going to have theta. Instead of initial velocity, we're going to have omega I t plus half the angular acceleration times time squared. Okay, so these are the big equations you should remember for linear and rotational motion. Okay, so let me actually draw a picture to help you understand some of these. So, for example, if a ball is moving linearly, then of course this is going to be its velocity. Its acceleration might also be in this direction, and the distance it covers looks something like this, right? So this is for linear motion. For rotational motion, you might have something like this. A ball is attached to the wall by some pin, and it's free to rotate. So this is its omega, its angular velocity, and its angular acceleration is something like that. And the amount of distance it covers is given by theta, right? This angular displacement here. Okay, so those are the main formulas you should keep in mind for linear and rotational motion. I might be missing out a few, so don't count me on that. But yeah, these are the main things. Okay, so the last thing I'll talk about is the last thing that I know anything about, and that's fluids. Okay, so let's talk a little bit about fluids. Unless anyone has any questions, you can stop me right here and ask any questions. Okay, so let's talk about fluids. Okay, so fluids. Okay, so what are I think we have a question in the chat, so, okay, yeah, no problem. So, what should you know about fluids? So, there's a lot of problems you can be given for fluids, but there are like maybe two very simple ideas. Just two things you have to remember for fluids, and that's the pressure equation and the Bernoulli's equation. And using those two things, and maybe a third thing I can't remember, you can solve practically any fluid problem. So the first thing you should know about fluids, is the pressure equation. Okay, so what do I mean by that? So let's say you have a beaker, or I don't know, an ocean, whatever, and it's filled with water, right? So if you've ever gone swimming, you probably feel a bit heavier, or you feel like there's a lot of pressure over you, right? Obviously there's a lot of water over you, and so that water exerts some force on you, and so there's bound to be greater pressure over here than over here, right? But we want to know how much pressure is there as a function of the height from sea level, okay? So here's the question we're asking. The question is, what is the pressure let me write it down here. What is the pressure? What is the pressure at a height h from the surface? Okay, so that's the question we're asking. What is the pressure in this fluid at a height h below the surface? So how can we figure that out? So let's say we have some distance over here, call that h, and I want to figure out the pressure here. So the pressure here at this point, I can go through the derivation, but I think we're running out of time, so I'm going to make this quick. The pressure at this point is going to be proportional to however deep you are, right? That makes sense, right? The deeper you go in the water, the more pressure there should be. So it's proportional to the height. And it's also proportional to the density of the liquid, right? So obviously if you're swimming in syrup, it makes sense you're gonna have a higher pressure than if you're swimming in water. So the density of the fluid also matters. And finally, what matters is what planet you're on. If you're swimming in a river on the Earth, you're gonna have less pressure than if you're swimming in a river on Jupiter, right? Because there's greater gravitational acceleration on Jupiter, right? So those are the three things that affect pressure: the density of the fluid, the gravitational acceleration, and the height from the surface. Okay, and if there's atmospheric pressure, if you're not in a vacuum, then there's going to be some atmospheric pressure P naught. This is your pressure equation right here. The pressure is equal to atmospheric pressure, which only exists if you're not in a vacuum, plus rho GH, right? Okay, so this is one of the main equations that you don't have to memorize. It's mostly straightforward. The second equation is Bernoulli's equation. So you want to usually use Bernoulli's equation when things are moving, right? When fluids are in motion. So let's go ahead and take a look at that. So, so fact number 2 you should remember about fluids, and that is Bernoulli's equation. So, okay. So what does Bernoulli's equation say? I don't know why it's not going down, but okay. So let's say you have something like this. Actually, I think the screen is not focused on what I'm writing. Yeah, that's weird. Okay. Okay, so let's say we have something like this. Okay. Okay, and so this is kind of like a weird pipe situation we have here. Okay, and so there's fluid in this pipe, right? Fluid moving through this pipe at some velocity. So we have fluid in this pipe. I'm just going to draw a little bit over here. So the fluid is moving with some velocity, I'll say V1 over here, and it's moving with some velocity V2 over here. The density of this fluid is rho, okay? That's the density of this fluid. What else do you need to know? Let's say the height from over here to over here. Let's call this height h. So let's call this height over here h. Okay, so Bernoulli's equation says the following. Okay, if I have an initial pressure of P and an initial, it's a kind of potential energy for fluids. If I have an initial pressure of rho GH and the initial kinetic energy of my fluid is half rho V squared, if I add all of these quantities up, this is going to be a conserved quantity, right? So, oh, I realize you can't see what I'm writing. Okay, so there we go. I scrolled over. So Bernoulli's equation says that if I take the pressure at some point plus rho GH plus the kinetic energy of my fluid, this is going to be a conserved quantity. So this whole thing at this point is going to equal the same thing at this point, right? So for example, if this is point 1 and this is point 2, then the pressure at point 1 plus rho GH plus half rho V1 squared is going to equal this same thing at point 2. Okay, plus half rho V2 squared. Okay, so this is what Bernoulli's equation says. So these are the two main things that you need to remember for fluids. It's the equation for pressure, which is rho GH plus atmospheric pressure if it's not in a vacuum, and Bernoulli's equation, which is kind of like conservation of energy for fluids. So that's it. I realize I've gone 20 minutes overboard, but that's basically most of the concepts that are going to be, I think, most of the concepts that might be important. So if anyone has any other questions, just now is probably the time to ask. Okay, awkward silence, and we're done. Okay, so thanks for coming. I will send this recording in an email to everyone, and good luck on the exam.